we've talked about a few of the different properties of stars. We're now going to have a look at a way that we can classify them, and we'll start off by looking at the Hertzsprung-Russell diagram, or HR diagram. The two properties that we're most interested in here are the one at the top, the temperature, and the luminosity on the side. You'll notice that the other two axes there, the spectral class is related to temperature. That's basically if we consider Wien's law, given that the temperature will relate to the wavelength of light that's most dominant. So the hotter the star, the more blue it is. The cooler the star, the more red it is. So you can see there's sort of the rainbow effect as we go through the main sequence there. On the left-hand side is the absolute magnitude. Now that's the brightness of the star if it was measured from a distance of 10 parsecs. It's similar, but in a way different to luminosity. Luminosity is actually is an intrinsic property of the star itself and is independent of distance, but there is a bit of a link between them. But as I said, we're going to focus on the temperature and the luminosity. Now, if we look at the graph itself, we can see then that you notice that the temperature scale is sort of back to front, so it's highest temperature on the left and lowest on the right. We can sort of divide it up into four. If we look at the extremes, I suppose, in the top right we'd have cool, bright stars. So stars up here that are they're fairly low in temperature, but they're very bright stars. So that generally will mean that they're going to be much bigger stars. Given that their temperature being low means that they wouldn't be radiating all that much energy. It means that they must be fairly large in order for for them to be bright. The top left, we're going to have hot, bright stars. So stars that are still quite hot, and as a result, they tend to be quite bright. And not necessarily always going to be large stars there, but just that the temperature could be the determining factor rather than the size. Bottom left, we've got hot, dim stars. So that means that we've got stars that are still quite hot, but they're not radiating much energy anymore, at least not in the visible spectrum. And then the bottom right, we've got cool, dim stars. So stars that are low in temperature and not radiating all that much energy either. You'll notice there that on this graph there's fairly obvious trends that you can see there. We've basically got it grouped into four sections. So we've got the white dwarfs that are sort of down in this bottom left-hand corner. We've got supergiants that sort of basically take sort of the top part of this graph. We've got giants that sort of sit through there, and then we've got the main sequence stars that form this band across the middle. We now need to sort of go through those classifications and be a bit clearer on what each of them represent. So we'll start with the main sequence. The reason we'll start with main sequence is, as the name suggests, it's where most stars can be found. So main sequence stars produce energy from fusion, and mostly so fusion of hydrogen and other light elements, not other light nuclei, sorry. And as I said, main sequence stars, nearly 90% of stars in the night sky, 90% of stars fall in the main sequence. The second group that we're going to start to discuss then are the red giants. So red giants being those stars that are on the right hand side. You'll notice that the majority of these, they do fall in the sort of the reddish to orangish sort of colour, known as red giants. Now red giants are actually they're cooler than the sun. So there's the first thing to mention. I should mention here as well that if we're talking about the sun, it would be sort of located around here. So generally speaking, these stars in the red giants are going to be cooler than the sun. They are much more luminous though. So we can see that they're higher on the graph, so they're much more luminous. And that then means that we can tell that red supergiants must be larger than the sun. Hence the name giants. And the next one then are the supergiants up the top. So if we've got giants and then supergiants, it makes sense then supergiants are even bigger again. So supergiants basically are just very large and very bright. and so if they're very large, they're known as supergiants, and as a result, because they're so large, they radiate a lot of energy. They're very bright as well. So if we look at those two combined, only about 1% of stars are giants or supergiants. So very few of the stars in the night sky fall into those two categories. Having said that, given the large number of stars that there are in the universe, it's still quite a lot of stars that fall into those two categories, but only 1% of the stars that we can see. The last category then, down in the bottom left-hand corner, are the white dwarfs. So as the name suggests, the white dwarfs, they are, generally speaking, sort of that whitish colour, so the range of wavelengths that they emit are fairly evenly spread across the spectrum. White dwarfs are actually remnants of old stars. You can think of them as being old dead stars, so stars that have used up their fuel source. So they're no longer really radiating energy as much. They're basically just sort of they're hot. They're fairly hot, and they're sort of slowly losing that heat. So they're fairly hot, and they're slowly losing that heat. They have low luminosity as a result of a small surface area. Which is also combined with the fact that they're not actually radiating light through fusion anymore. And as I said, they take billions of years to cool down. Now, white dwarfs, if you go through and do the maths, they are about 9% of all stars. Now, if we go back to just look at the Hertzsprung-Russell diagram one more time, you can sort of see these different groupings of stars. It's not that this is a static diagram as such. We won't see much change in our lifetimes, but over sort of millions of years, you'll actually see that as stars use up their fuel sources, they'll sort of move through these different groups. So the Sun, for example, will eventually become a red supergiant. So we'll have a look at that in a later video. But the stars will actually sort of move through this graph as their luminosity and temperature changes throughout the lifetime of the star.